So in the last module, we saw the different layers of network based on the functionalities, and we discussed a little bit detail of the physical layer and the data link layer and the difference in the layering in case of optical fiber networks. We introduced this SDH, SONET kind of framing multiplexing techniques to make use of the high bandwidth of the optical fiber. Today we are moving on to the next topic, which is the different categories of optical network. So this is the bigger picture, the functional block diagram that represents the different categories. So starting from the bottom, from the end user network, you could have the fiber to the home, which is giving you internet high speed bandwidth, and it could be your cable TV or it could be your telephone network, the mobile network. You could also, the last mile client could be the enterprise clients, which is big offices or data centers and so on. So this network which is in the last mile is what is called as the access network. The lengths are typically less than 20 kilometers and the data rates are typically 0.1, which is 100 Mbps to about 10 Gbps. That is what is currently happening. Though towards the end of the module, you will realize that the mobile front haul network is actually using much larger data rates. Now, these get connected to the metro network, which is operating at a slightly higher layer. So, each of the node of the metro network could be dropping off to different access points, and that is generally called as the wide area network, and the distances are about 100 kilometer to 200 kilometer or so on, and the data rate is less than 10 terabits per second. So you can think of it as an aggregate of all the access network traffic which could be going through your metro network. And then of course you have the global network, which is the what is also called as the core network, which connects the different metro add drop points, and these are the network which actually handle communication between intercontinents. So very long distance networks are handled by the core. So you can imagine that one of the operating nodes of this core network may be dropping off at specific metro network and so on. Typically, the length of the core network is of thousands of kilometers. The data traffic is about several terabits per second, because you can imagine that the aggregation of metro is what is getting into the core line. And of course, these are since these are long distance communication links, these optical fibers would have regenerators, it could have optical amplifiers and so on. Wavelength division multiplexing wavelength division multiplexing is a technology that could get used in metro networks also, and of course it gets used in the core network. The lengths that we are talking about, that the length of the metro network is about hundreds of kilometers, etc. It's not really absolute length that we will talk about. So for example, this is the open source data available for the metropolitan area networks in the UK. Since they are placed between the local area networks and the wide area networks, the size actually substantially differs from case to case. It depends on the volume of traffic, it depends on the nature of traffic, it depends on how the network is evolving, it depends on how the distribution is there in population. Suppose in countries like Australia or where the density of population is very low, you could have really long lengths of fiber which handles the metro network. So what is typically done for different countries is, this is for example a map that is available for UK. So what is commonly available in open source is the path length of the metro network for different links, and the number of occurrences of such path length is what is plotted in this figure. This frequency does not mean the frequency or bandwidth of transmission, it just means the number of times this kind of link lengths are available. And it turns out that on an average, the cumulative frequency is what is shown here. So on an average, the path length is more for lengths which are 200 or between 100 to 200 kilometers. So this cumulative frequency plot helps us to understand here better. So for instance, if I take 90% line here, it simply means that 90% of the metro network in the UK is less than 300 kilometers. That's what this means. So this is again a relatively very sparse population density as compared to, for example, like India. So the metro networks are actually, the distances are slightly longer, whereas in case of India, the point-to-point link distances in the distance between two add-drop multiplexers in the metro network could be much smaller. So to give an example, this is the multiple 10 gig connections which connects all the state capitals. So this is a typical example of a metro network in India, and this is also referred to as the National Knowledge Network. More than 1600 colleges, universities are connected through the National Knowledge Network. So National Knowledge Network is actually the physical layer fiber infrastructure that is laid between different state capitals so that high-speed connectivity is ensured between these places. And turns out that, so the map here shows that how this connectivity is happening, and it is given gigabit connectivity, 10 gig connectivity to all the 640 districts is what this NKN map shows us. Here again, the distances, you see that it could be very small or it could be large, for instance here, or it could be even very large from here to here. So the point is that the length scale is not really absolute. It may vary depending on the volume of traffic and depending on the density of population. The question is, you see the interconnection between the access network, metro networks, and the long haul networks or the core networks. You see that physically how this fiber connection is laid between the nodes where the data is added or dropped can be done in multiple different ways. For instance, if you take the case of long haul networks, you see that the different nodes are connected something like a mesh here, okay? And you could also have long haul networks where there is a backbone provider which have connected in like a ring kind of configuration. The different nodes get connected in a kind of a ring configuration. So here specifically we are talking about how the different nodes get connected to each other in the physical layer. For instance, if you take a residential network, you see that you have one connection coming in and then there is like a branching like a tree. Here again in this access network, you see something like a ring and so on. So based on how the different node points are connected with each other, the optical network topologies can be classified as, the physical topologies. And then of course, based on how the signal finds its way, you could have the signal topology and the logical topology. So physical topology actually refers to the way the wiring is laid out, the way the nodes are located, and how these nodes are interconnected. Okay. Whereas the signal topology need not really follow the physical topology. Depending on where your transmitter is and where your receiver is, it may follow a slightly different topologies. So now we spend a little bit time on what are the possible physical topologies, and the simplest physical topology is a point-to-point link. Let's say I want to connect from my server in my office to the computer in my home, and my office and home is separated by, let's say, half a kilometer. The simplest way of establishing a very fast link is to just do a point-to-point link. So such point-to-point links do exist for dedicated connectivity between two locations. A typical example could be a connectivity between a hotline between, for instance, the president's house to, or the president's residence to the prime minister's residence. Okay, so that is a point-to-point dedicated link. It's a very permanent kind of link. You may not be using the resources of the link optimally because it's just active whenever you have a transmission happening. But these are dedicated links, and there are specific applications of these kind of links. A slight modification is to have actually multiple users or multiple nodes for this point-to-point link, and depending on the demand, there is a switch that connects between, for instance, you have a node A and node B, and let's say there is a connection requirement between node A and node B, the switch will turn on this connection, and once that communication is over, this is like a circuit switched communication, and let's say there is now a demand between connection between node B and C, then the switch basically turns on this connection and so on. So this is how a point-to-point link can be set up, but it's slightly in a dynamic fashion. So this is the next higher level in terms of network topology. And conventional telephone lines, in the olden day telephone lines, the land lines used to get connected this way. For example, if you want to connect from you're dialing a number, there is a telephone operator or the telephone service provider would have a switch in the central office of the telephone operator. That switch actually switches the physical path towards your destination, and multiple such switching happens, and that's how a connection gets established. The next modification, which is again very commonly used, especially in computer networks, which could also be there in fiber optic networks, is the bus topology. So a linear bus is where you have an optical fiber connection like this, right? So the green line is actually showing the optical fiber. You could have drop points at different nodes, and these nodes could further connect to users through a tree network, or these themselves could be different users. So that's where the same transmission medium actually services simultaneously to different nodes. Distributed bus is where you can slightly improve the number of nodes or number of users, where you can split, you can add a branch. So here you had just two endpoints, but now you can have a third endpoint where you have added a branch. So this is a splitter where the fiber is part of the power is taken out, and then you are servicing it to multiple nodes or multiple users. The advantage is that this is how typical in access networks. This is how one way of typically implementing access network. It's very cheap and easy to implement. You can keep adding or dropping nodes. It requires very less cable because when compared to the case where you need a physical cable between any two nodes, here the amount of physical cable required is very less. But the disadvantage is that whenever you are adding or dropping nodes, the link budget gets affected, because let's say you suddenly are adding node in this physical location, you are tapping out some power from this location, which means that the power that is available to the remaining part of the network in the downstream starts getting affected, which means that you have to do your power budgeting, link budgeting once again. The other major issue is that let's say there was a break in cable here, it will turn out that that will prevent communication down the stream, right? So the related issue is that it becomes very difficult to troubleshoot. For example, if this node is not working and if there was a cut here, you will have to really figure out where exactly, you have to look at the health of all the other nodes to figure out where exactly the failure has happened. But again, this is again one of the popular ways of connecting different users or connecting different nodes. The third common topology is what is called as a star topology. So in a simple star topology, you have a central node and that is connected to so many other nodes. So which means this much of cable is being required. But each connectivity between the central node and each other node is independent of each other, which means you can immediately recognize that if there is a cable cut here, that's not going to affect any other user, any other node. So that's a star topology. Now you can find extension of this star topology as an extended star, where you say that if you want to connect, you want to carry out the same topology to connect to more number of nodes, you will have to worry about the path, the quality of the signal. You may want repeaters. So you could have two central nodes. So this is central node 1 and central node 2 connected with each other, to each other with a repeater. So that the signal that, let's say this from this node you want to communicate, this is the node A and this is the node B to which you want to communicate. It can go through this central node and the signal can find its way through the repeater to the other to the destination B through the second central node. So this is an extended star topology. You can keep adding users through this topology, or it's not necessary that you need to club two star networks. You can kind of combine topologies and say that this central node is actually a part of this bus topology. Okay, so this bus is central line of the bus services the central node, and the central node can now service multiple users. So that's a typical example here given. It's a distributed star where there is no repeater. It's like a daisy chain, continuously one after the other. So these are variations. The good thing about the star network is that you can keep expanding the network without disturbing other nodes, because if you were to expand this, you have to without really disrupting the other node, because this connectivity is established. All what you want to make sure is that you have sufficient receiver sensitivity to handle the other node. The cable failure, as we said, affects only a single user or a single node. It's very easy to troubleshoot, because if this node is not working or if there is a fiber cut here, you need to go and check only this part of the network. You don't have to physically go and verify all the other parts of the network. And corresponding to this advantages, the disadvantages that because each node is connected to other node with a fiber, the amount of cabling is really large. A break in main cable will prevent, like in the previous case, if there is a break in this cable, it will prevent all the other nodes from getting the signal. It's very difficult to implement because laying cable to all the nodes is slightly difficult. The most popular or commonly used topology in an optical fiber network is a ring topology. Now, in a single ring, you have, so you could have single ring and a dual ring. We'll talk about dual ring in a while. In a single ring, what you have is that each node, so this is node A, B, for example, C, D, E, F. Each node gets connected to all the other nodes through this path. All the data between the nodes travels. So, for example, you want to transmit from A to D. Is the communication that you want to establish. So it means that depending how the ring is configured, you could have data going clockwise. It goes through all the nodes until it reaches the point D. Okay, there's no other path. So this is one way of implementing a node. Typically in the the first version of the ring topology, the data flows only in one direction. Of course, there are variations for this. For protection, we will come to that when we talk about protection. But this is the idea of a single ring topology. Data keeps circulating only in one direction, and the data to be transmitted between any node to any node will pass through all the other nodes. Okay, so the other nodes will have to, all the nodes will have to check and say whether depending on the header, decide whether this data was meant to be distributed here or whether it is supposed to be forwarded. Now, in case of dual ring, as the name indicates, there are two connections between two neighboring nodes. So, for example, node A and node B gets connected with two optical fiber links. The data will flow in two directions in the two rings. Generally, depending on what configuration you are using, data flows only through one of the fiber. The other fiber is supposed to be for protection. Okay, we will talk more in detail about protection. So the advantage is that if there is a failure, let's say, so even here from A to, let's say you want to transmit data from A to E, you will have to go through all the nodes through this network fiber to reach E. Okay. Now, when there is a failure, for example, in this ring, this part of the network, what happens is at C, the node C has already identified that there is a failure. Now, how does a node identify there is a failure? You have devices called as OTDR. OTDR is optical time domain reflectometer. There are these ranging devices at each nodes which will keep looking for the health of the node. So, if there is a fiber break, light from the point at which the fiber is broken will get reflected back, and that reflected light is captured by this node, and the node can always establish that there is a fiber cut. So, whenever there is a fiber cut, the node recognizes it, and then what happens is the data is redirected. Whenever there is a cut, the data gets redirected through the protection fiber, and then it reaches the destination, which is E, through the protection fiber. Okay. So, this is the advantage of dual ring architecture. It will bypass the primary ring, and it will continue to do that until somebody comes and actually physically splices the two fibers. So, the advantage is that the cable faults can be easily located because effectively one node is connected to the other node. So, any node is connected to two neighboring nodes. So, each node can keep track of what is happening to the connectivity between the neighboring nodes. It is moderately easy to install as compared to a star network, for example. But the problem is that the network planning has to be done very meticulously. You cannot keep adding nodes in a ring, because if you are trying to add a node to this ring, the existing network needs to it will get disrupted. A single break in the cable can disrupt the entire network, for instance. So, the most failure resistant topology is probably the mesh topology. In a fully connected mesh, every node is connected to every other node. Okay, as simple as that. So, you could, this is very useful for packet switched network, where you can now find multiple ways to reach. For example, this is my A and B, and you want to move from A to B. There is a direct connection between A to B available. If that fiber is cut, you can go from this node to this node to this, or you can go from here to here to here. All kinds of possibilities are possible. So, this is like the most tolerant, the most resilient kind of network. So, data can be simultaneously transmitted from any single node to any other node, but the problem is that it's very costly, it's very complicated to implement this, because you have too many fibers that needs to get implemented. So, that's a fully connected mesh. A compromise is a partially connected mesh where you do partial connection depending on the traffic predictions. For example, this is again very commonly used in metro networks. In traffic predictions, you know that maybe the traffic between, for instance, Hyderabad and Bombay, for instance, is very high. The traffic between Delhi and Bombay is very high. So, you will, for all these points where there is a large traffic expected, you will provide multiple paths. But for instance, where the traffic between district headquarters, or maybe the traffic between a more remote point is restrictive, then you may not really, in a remote place, for instance, you may not be very worried about providing multiple connections, right? So, it takes the advantage of redundancy provided by the mesh network, but the cost and the complexity is slightly reduced, because now you are intelligently planning which nodes require redundancy and which doesn't. Okay. So, this is the mesh one, and of course, the advantage is that you can keep expanding this network, because every node is independent of every other node, and hence you can keep expanding this. The disadvantage, as we said earlier, it's a very complicated implementation. It's a costly implementation, but a lot of metro networks tend to get implemented as a mesh topology, as we have seen, for example, here. you see that the long haul networks get, because of this advantage with redundancy, the long haul gets implemented as mesh in the mesh topology. Similarly, the metro network also gets implemented in the mesh topology, which you are seeing for instance here. So this is a mesh topology. The NKN network is a classic example of a mesh topology where every node is actually getting connected to the different nodes where the connectivity is more. So Delhi, for instance, has connectivity to mostly all the district headquarters. Srinagar, for instance, has connectivity with, for example, Jammu. It has connectivity to Chandigarh, and from there you have connectivity to Delhi, right? So this is a classic example of the case where you are using partially connected mesh. Last but not the least, which is getting most commonly used these days, is the tree topology. And the tree topology gets implemented in the access network, the last mile network, and especially in data center networks. Now, what are these data center networks? You would have the cloud, the servers which are handling the cloud services. They are all physically located in a given place, and you will have some huge computers or huge servers. When I say huge, it's the data rate that they handle. They need to be connected, and they need to be connected to the local access point. And you could also have, so this is a node corresponding to the access network, and corresponding to that, this will get connected to a access point of a metro network. And you could also have independent data centers which are geographically located in slightly different locations. When you make a file search maybe, or when you are putting it in your cloud and you're trying to referring to multiple instances, so what also needs to happen is the connectivity between the data centers, right, which could happen through the access here. So this connectivity, the data center connectivity, the network in a data center is mostly implemented in the tree topology, where it's highly hierarchical. There is a central root node at the top level of the hierarchy. This gets connected to multiple nodes, and each secondary node, depending on the number of servers that you're handling, may get connected to third level nodes. And the branching factor tells you how many lower level nodes are connected to a given node. The data center networks typically, as I said earlier, the topology used is called as a fat tree topology, because the stem of this is really fat. We will talk about it a bit later. So how do you choose which topology should I implement? So as a network implementer, what you need to worry about is first geography. How far are these nodes where you're adding or dropping channels are? What is the bandwidth required at each node? What is the efficiency of resource sharing with minimum blocking probability? You should not, you should provide enough number of alternate paths such that if one of the path is busy, you should be able to use alternate paths. Then related parameter is the quality, and it is the flexibility of services. Of course, the cost has to be minimized, right? So in addition to this topology, so any kind of network that you lay, it will belong to one of these topologies. Or you could, as we said earlier, you could combine, for instance, star with a bus, or you could combine with a tree with a ring, and so on. So you can choose combinations, and all possible ways you are connecting these nodes will fall under one of these topologies.